functions of several variables on this tape, and also some new concepts that will be used for this purpose. In particular, we'll be looking at the gradient, and prior to the gradient, we want to take a look at what's called the directional derivative. We'll do this for functions of two variables at first, although it also holds true for functions of more than just two variables. First of all, if we've got a vector u, which is a unit vector, and a function f of x and y, we want to talk about the directional derivative in the direction u of f at x naught, y naught, where x naught, y naught is a particular point in the plane. If the unit vector here, u, has a given direction, we've got the graph of f above this point and in the neighborhood of the point. And what we want to know is, what's the rate at which the function is increasing in the direction u? So the directional derivative of f in the direction u is the limit as h approaches 0 of f of x, and here I'm going to use the vector x. In fact, I'll use x naught here for the vector x naught, y naught, and in general here, x for a point xy with the vector notation above it. So this is going to be f of x, in this case x naught if we're interested in x naught. If we're interested in a general point here, xy, then f of x plus h times u minus f of x, that's say the function at the point x, divided by h. And this will then define the directional derivative in the direction u of f at x, which you can use this notation for, or sometimes this notation is also used. F prime sub u at x. So what happens here? You just take this vector u, you multiply it by a small quantity h. Look at the difference between the function at the nearby point and the function at this point. Divide by h, so we get a slope here, so to speak, and take the limit as h approaches 0. Since f is a real valued function, the numerator and denominator here are both real numbers, and I'll take the limit as h approaches 0. We won't generally be computing directional derivatives directly. That's to say, if you do try and compute this limit for a given vector u, you end up with something that's a little bit on the complicated side. However, let's note the following, that the partial derivative of f with respect to x at a point x is the directional derivative in the I direction. So if u here is I, then the directional derivative is the partial with respect to x. If u is equal to j, then the directional derivative is the partial with respect to y. So this is the partial with respect to y is the directional derivative in the I direction of f. Or if you want, you're using the other notation, the derivative in the I direction of f at x. Okay, what we're going to use in order to compute the directional derivative is what's called the gradient. And it's defined as follows. So here's the directional derivative. The gradient of f, that is, well, it is a function, it's a vector, it's a vector at a specific point here. It's an x naught, y naught, it's a vector. And consequently what it is in general is, if we look at various points x naught, y naught, is that it's a function which assigns a vector to each point x naught, y naught. Right? As follows, if there is such a thing. The gradient is a vector, if there is one. So that, and it's written, gradient of f at x naught, y naught, and you can indicate this by putting a vector sign above this upside down triangle here, or you can leave it off, right? This vector is to satisfy for each vector h, right, or for vectors h, f of x naught, let's say this vector h is h1, h2, plus h1, y naught plus h2, minus f at x naught, y naught, is equal to the gradient of f at the point, or better, perhaps, minus the gradient at the point, dotted with h, is equals to epsilon of h times the magnitude of h, where epsilon of h goes to 0, as the vector h is allowed to approach the 0 vector. Right? Or in vector notation here, this is f of the vector x plus the vector h minus, well, if we're at a specific point x dot here, minus f at the point x dot minus the gradient of f at the point dotted with h is equal to, so this is the vector here, is equal to epsilon of h times the magnitude of h. Right? So it's a vector here that satisfies this. And when we see the properties of this vector, we'll see that we can use it very easily to evaluate the directional derivative at any given direction u. Okay, we have now the gradient, and let me give this in general here at any point x. The gradient of f at x is a vector which satisfies, if there is one, f of x plus h minus f of x minus the gradient of f, and the gradient's a vector, so let me indicate that, at x, dotted with the vector h, is equal to epsilon of h times the magnitude of h, where epsilon of h approaches 0 as magnitude of h approaches 0, or as h approaches the 0 vector. So this is the gradient. And now let's consider a vector u, a unit vector, magnitude of u equal to 1. And let's suppose f has a gradient. At, let's say, at point x. Then what we want to do is we want to take a look at the limit as h approaches 0, f of x plus hu minus f of x divided by h. And recall that this is the directional derivative in the direction u of f at x. Okay? Well, we've got that f of x plus hu minus f of x, since f has a gradient, if we let hu be the vector h, that this is going to be equals to f of x plus, this is going to be equals to the gradient of f at x times, or dotted with, hu divided by h plus epsilon of hu, magnitude of hu, right? And now we've divided by h throughout here, so we're going to divide by h. So this is, from the definition of the gradient, this f of x plus h minus f of x is equal to this, plus this epsilon of h times the magnitude of h. All right? Well, the magnitude of hu is h, so we can cancel the hu with the h. Right? The magnitude of the h here is also h, so we can cancel the magnitude hu with h. Canceling this is not quite right here. Right? This is a dot product. The dot product with this h, I can cancel this h with this h because I can bring the h outside of the dot product. So I still have then here that this is equal to the gradient of f at the point x dotted with u. The h's here cancel, and over here this h cancels with the magnitude of hu, and as h approaches 0, this approaches 0. So this limit as h approaches 0 is this limit as h approaches 0 of this quantity, which is equal to the gradient of f at x dotted with the vector u. So if we knew how to find the gradient, we could then find the directional derivative in any direction u by simply dotting the gradient with u. However, right, finding the gradient is not a big problem. Notice what happens here. If we let u equal I, then the directional derivative in the direction I, which is the partial with respect to x at the point, is equals to the gradient of f at this point dotted with I. We let u equal j, then the partial derivative with respect to y is the directional derivative in the j direction at the point. It's going to be equal to the gradient of f at that point dotted with j. What this says is that if f has a gradient, then the partial with respect to x is its I component, and the partial with respect to y is its j component, so that consequently the gradient of f at a point x, right, is a vector which is going to be equals to, if it exists, the partial with respect to x at that point, I, plus the partial with respect to y at that point, j. dimensions, there'd be the partial with respect to z times k. Right? So, in order to compute the gradient, we simply take the partial derivative f with respect to x and the partial with respect to y. The first one is the I component, the second one is the j component, and that's going to give you the gradient, if the gradient exists. Now what we need to know is this, that if partial with respect to x and the partial with respect to y are continuous functions, then the gradient automatically exists. If the partial derivative exists and are continuous, then the gradient exists, and this is what it is. All right? We're not going to prove that fact. It's generally considered to be subject matter for more advanced calculus. However, we're going to use this to compute the gradient. We can do it very quickly now. Let's take a look at computing the gradient for a specific function here. Let's let f of x and y be equals to x squared plus 2y squared. Right. This is a paraboloid. The graph is a paraboloid. If this is z equals to x squared plus 2y squared, then when y is equals to 0, f is x squared, and so this looks like this. X squared, z is equal to x squared over here. When x is equals to 0 in the y plane here, it looks like y is equal to 2x squared, and the result is a paraboloid that looks something like that. All right. Let's take a particular unit vector here, u. For simplicity here, let's look at 3/5, 4/5. Right? 3 squared plus 4 squared is 5 squared, so this is a unit vector. And let's look at a specific point here. Say 1, 2, 2, 1. Let's do 2, 1. So let's let x be the point 2, 1. And then the gradient of f at 2, 1. Well, first of all, at any point x. We need the partial of this with respect to x. That's 2x. That's the I component of the gradient, plus 4y. J is the j component. So this is the gradient then. Partial with respect to xi plus partial with respect to yj. Right? The gradient of f at 2, 1 is equal to 4i, to put 2 in here for x and 1 in for y, plus 4j. About the directional derivative in the direction u of f at 2, 1. Well, this is equal to the gradient of f at 2, 1 dotted with the unit vector u, which is going to be equals to 12/5 from 4 times 3/5 plus 16/5 or 28/5 is the directional derivative at this point 2, 1 of the function f. In fact, if we wanted the directional derivative at any point x in this direction u, it would be equals to gradient of f at x, 2xi plus 4yj, dotted with u. So it would be 3/5 times 2x plus 4/5 times 4y. If we had a direction v that we were interested in here, you can always get a unit vector in a direction v by taking v and dividing it by the magnitude of v. So creating a unit vector in a particular direction here is not difficult. And then if you want the directional derivative in that direction, you compute, the easiest way to do this is to compute the gradient and take the dot product of the gradient with the unit vector. Let's take a look at this gradient just a little bit more. gradient represent? Well, let's let U be a general angle here, a general unit vector. So any unit vector here at a given point, instead of 2, 1, think of this as the point x. Right? And the directional derivative in the direction u of f at x is equals to the gradient of f at x dotted with u. Right? Remember, the gradient is a particular vector here. This might be the gradient of f at this point x. Now, by the definition of the dot product, this is equals to the gradient of f at x, the magnitude of x, times the magnitude of u, times the cosine of the angle theta between those two. So if this was our vector u, and this angle here was theta, then the directional derivative in the direction u is the magnitude of the gradient. Magnitude of u is 1, cosine of theta. Right? Well, this is going to be maximal. Since this is 1, this is going to be maximal when theta is equals to 0, because then cosine theta is 1. Right? du of f at x is maximal. It's going to be minimal when theta is pi, so that we get minus 1 here. Right? And du is maximal, and the magnitude of the gradient when theta is equal to 0, the magnitude of the gradient right, is equals to the maximal value of the directional derivative. Various values of u. So what this says is this. What is the gradient vector then? It's a vector, right, which points in the direction in which the directional derivative is maximal. And, moreover, the value of the gradient, the magnitude of the gradient, is the value of that directional derivative in the direction in which it is maximal. So the gradient then has this interpretation. It's a vector at the point that points in the direction of maximal increase of the function, and the value of the gradient is the rate at which that increase occurs. So that, for example, at this point here, this is wrong. The directional derivative is maximal when the vector leaves, goes away from the origin, or more away from the origin at least. The gradient vector will be pointing in some direction more like this, right? Indicating the direction in which the increase in the function f is maximal, and the magnitude of the gradient will be the magnitude of that increase. We're going to want to look at maximum and minimum of functions. And for this purpose, we're going to want a couple of definitions. One, the absolute maximum of a function, a minimum of a function, and also a local maximum and local minimum. And these are analogous to the similar situation for functions of one variable. And they go like this. F of x and y is an absolute maximum at x naught, y naught if less than or equals to f of x naught and y naught. Right? For all the x and y in the domain of f. F at x naught, y naught is bigger than or equals to all of those. Okay? This means that there can be some ties. That's to say there can be other values, x, y, where f of x, y is equals to f of x naught, y naught. If you don't want any ties, then you talk about a strict absolute maximum. That's to say, if f of x naught and y naught is larger than f of x and y, when, of course it can't be larger than itself, when x naught, y naught is not the same point as xy, is not equal to xy. Right? You talk about a strict absolute maximum. Right? And we can also talk about a minimum. Right? For minimum, right, you want to just replace this inequality by the other way around. And also talk about a strict minimum, or strict absolute minimum, by replacing the inequality greater than or equals to with the inequality greater than. F of x and y as a maximum on a set of points E if, let's say at x naught, y naught, if f of x and y is less than or equals to the value of x naught and y naught for all x and y, right, with x, y, and e. And here we're talking about an absolute maximum on E or a maximum on E. We can also clearly talk about a strict maximum if we replace this by less than for all other points, x, y, in E. We want to talk about what's called a local maximum, a local minimum. F of x and y said it have, so it has a local maximum, right? And local minimum is similar. It's the opposite, actually. It has a local maximum at point x naught, y naught, if there is a circle of radius, a disk, if you want, centered at x naught, y naught. It's a circular disk, if you want, centered at x naught, y naught. Perhaps just a small one, but if there's a disk so that f has a maximum at x naught, y naught on this disk. So that means that there has to be some circle centered about x naught, y naught, and so that our function here, even though it may be larger elsewhere, takes on its maximum on this disk at the point x naught, y naught. And we can also talk about strict maximum, strict local maximum. We can also talk about which means that what it has its minimum on this disk, and we can talk about strict local minimum if it has its minimum on the disk, and no other point has a function value equal to it on the disk. So here are some definitions that absolute maximum, and of course absolute minimum, the maximum on a set, and a local maximum. I'm going to take a look at the analogs of max and min problems for functions of one variable and functions of two or more variables, and an analogous theorem holds there. If f of x and y, use two variables for an example here, is continuous on a closed region, by that is meant a region in the plane with the boundary included, so that, for example, something like this region A here, including all the points along the boundary. Then, so this is in a closed region A, then f takes on its maximum and minimum on A. That's to say there is point x naught, y naught, where the function is minimal. There's another point x1, y1, where the function is maximal. Right? Now there may be ties. There may be several points where the function takes on the maximum value on the interval. This also implies that the function is bounded on the interval. That's to say there's a strict maximum value that is not, so it's not larger than that value at any point. Okay, this is the analog to the fact that on a closed interval, a, b, a continuous function takes on its maximum and its minimum. So that, for example, here would be where the maximum occurs, and here would be where the minimum occurs. Okay, now there's another analog here. In this case right here, there are only three possibilities for the maximum and the minimum. So say the maximum can only occur at the endpoints, A and B, points where the derivative does not exist, abbreviate that by D and E, and points where the derivative is equal to 0. So what you normally do is you check all three of these collections of points to find out where the function takes on its maximum or minimum. And actually, this is true of a function whether it's continuous or not. That's to say, these are the only points where it can take on its maximum or minimum. The same type of thing holds here for functions of several variables. If f of x and y takes on its maximum or minimum at a point x naught, y naught, then one of these three things must be true of x naught, y naught. Right? One, x naught, y naught. Let's say that this is in A, is on the boundary of A. By boundary of A, we mean a point here in A disk containing that point, there are points at A of the disk, and there are points that are not at A of the disk. So one possibility is that the function takes on its maximum, let's say, on the boundary. That's the analog to the taking on its maximum on one of the two endpoints. Second possibility is that one of the partial with respect to x at the point, or the partial with respect to y at the point, does not exist. Again, DNE for does not exist. It's possible that one of the partial derivatives doesn't exist at the point. For example, the function may have a peak like so, in which case partial derivatives wouldn't exist, and that's the analog here to the derivative not existing. If one of them doesn't exist, then it's possible that you have a maximum there, or a minimum. The third one is, right, and the only possibility left is that you're looking at a point that's inside region A, and both partial derivatives exist, and in that case what must happen is the partial with respect to x at the points x naught, y naught, and the partial with respect to y must both equal 0. So the partial with respect to x at x naught, y naught is 0, and the partial with respect to y at x naught, y naught is 0. Right? The reasoning is the same as it is for functions defined on an interval. That's to say, if the derivative was not equal to 0, let's say it was positive, then there'd be points to the right where the function was larger, and points to the left where it was smaller. So this couldn't be either a maximum or a minimum. If the derivative didn't exist and it was negative, for example here, then there would be points to the right where the function was smaller, and points to the left where it was larger, and so that couldn't be a maximum or minimum. This says, if you like, that if the function has a tangent plane at the point, that the tangent plane has to be horizontal. Another way of saying the same thing here, in the event that the gradient exists, is that the gradient must be the zero vector. The gradient of f at x naught, y naught must be equal to the zero vector. That's to say, there's no increase in any direction away from x naught and y naught. If the gradient were not equal to 0, then its magnitude, which tell you the rate of increase in the direction of the gradient, and that would say that there were points in that direction where the function was larger, and in the opposite direction there would be points where the function was smaller. So these three things here, these are the points where you look to find a maximum or minimum of a function on an interval. We're going to take a look now at a specific function of x and y and determine where it takes on its maximum and minimum. We'll actually take a look at the function on the entire plane because of the fact that the function is going to take on a maximum on the bounded part of the plane. Let's take a look at a simple example. 1 plus 2x cubed, let's say, plus 3 y cubed minus 4 x to the fourth minus 5 x to the fourth. The graph of this is going to look something like this. At 1 it's 1, and it's going to take on its maximum. And for large values of x, and also negative values of x, and large values of y, and negative values of y, the function is going to be very negative due to the fact that you've got an x to the fourth term, a minus x to the fourth term, and a minus y to the fourth term here, which make the function, they dominate the function and make the function negative when x is large or when y is large. So even though the theorem says that we should be looking at closed regions and their boundaries, we can now here look at the entire plane, and if this is f of x and y, right, it's this maximum is going to occur somewhere on the plane. And to find it, since the function has got partial derivatives at every point, we want to take a look at those partial derivatives, and in particular when they're equal to 0. So the partial with respect to x of this is equal to 6x squared minus 16x cubed. Right? And the partial with respect to y is equal to 9y squared minus 20y cubed. Right? We want to know when these are equal to 0. Well, partial with respect to x is going to be equal to 0 when we factor x squared out of here and divide by 2. We'll have 3 minus 8x times x squared is equal to 0. The partial with respect to y is going to be equal to 0 when if we factor y squared out of here, we've got y squared times 9 minus 20y is equal to 0. So this is going to be the case when x is equal to 0 or 3/8. And this is going to be the case here when y is equal to 0 because of this factor, or 9/20. So this gives us 4 points where the maximum or minimum could occur. 0, 0, 0, 9/20, 3/8, 0, and 3/8, 9/20. So what we want to do is determine what f of these points is. Now we can do that very simply here by just putting this back in here. We know that f of 0, 0 is equal to 1. All right, putting these values in here for x and for y and seeing what the result is. Let's take a look at the situation, though, rather than just calculating this, because the arithmetic would certainly be complicated here on the board. F of x and y is equal to 1. Now, if I collect the x terms together here, I've got plus 2 times x cubed times 1 minus 2x. All right? 1 minus 2x times 2x cubed will give me these two terms. And then I've got plus, for the y terms here, I've got y cubed times, 3 minus 5y. And now, let's take a look at what happens if we put 3/8 in here for x. We end up with 1 minus 2 times 3/8, which is equal to 1 minus 6/8, or a quarter. And so this will be a quarter, this will be something positive, and we'll be adding something on to the value of the function, the number 1 here. And so it's going to be, we're going to get larger values if we move to the point that has 3/8 in the x position. The similar situation here holds with 9/20. If I put 9/20 in here, I get 5 times 9/20 from 3. This is equal to 3 minus 45/20, right? Or 60/20 minus 45/20, or 15/20, or 3/4. All right. So that consequently, if I put if the value 9/20 is in here for y, I'm going to get 9/20 cubed times this quantity, and it will be larger. So that whatever this value here is, this is the maximum. That's to say, putting 3/8 in here for x and 9/20 in for y is going to give a larger value than putting 0 in for either one of those two. So this is going to be the maximum here. Now this is not a minimum. The function does not take on its minimum, and this point right here, 3/8, 9/20, is where the maximum occurs. I want to take a look at an applied maximum problem, a simple one. A situation where you've got something that depends on several variables and you want to determine where the maximum occurs, where the minimum occurs. Right? In this case, let's imagine that we wish to make a box like so, with an open top. Right? And let's suppose that the cost of this box is going to vary in the following fashion. Suppose that the bottom is going to be $3 per unit area. The ends of the box are going to be $2 per unit area. And the sides of the box are going to be $1 per unit area. Right? And let's suppose that the box is supposed to contain 24 cubic, let's say feet. So that in which case this is $2 per square foot, $1 per square foot, and $3 per square foot. For the bottom, $1 for this two sides and $2 for the other sides. Then what we wish to do is minimize the cost of the box. All right? So what have we got here? We've got the cost is equals to, if we label the upward direction z, let's say, the forward one x, and the one to the right and left y, then the cost is going to equal, what? $3 times xy for the bottom, plus 2 times $2, because there are two ends to the box, times xz, plus 2 times $1 yz. Now, we also know that the volume of the box is 24 cubic feet, so we've got x times y times z is equal to 24. We want to write this with as few variables as possible here, and here we can use this factor right here to remove z from this formula, because z is going to be equal to 24 over x times y. So we now have the cost is equals to 3xy plus 4 x times z is going to be times 24 over y plus 2. Y times z is going to be 2 times 24 over x. The y's will cancel. So now we have the cost here, and it's a function of x and y. Right? The next thing to notice is that this cost is going to take on its minimum. The cost makes sense only for x and y positive, and it's going to take on its minimum somewhere in the first quadrant, because if we let x or y get large, the cost is going to get large because of this. On the other hand, if either x or y are small, the cost function here, because there's a y in the denominator here and an x in the denominator here, the cost is going to get large. So somewhere in a rectangle here, with large x and y values excluded, and with real small ones excluded, the minimum is going to occur. Okay, at the minimum, we want to take a look at the partial derivatives with respect to x to find the minimum, and the partial derivative with respect to y of this function. The partial derivative with respect to x is equal to 3y, right? 0 for this, plus 48, and then this is x to the minus 1, so it's going to be times minus 1, x to the minus 2. Partial with respect to y, at each point x and y, is going to be equal to 3x plus 96 here. This is y to the minus 1, so it's going to be minus 1, y to the minus 2. The partial is 0 for 48 over x. So we want to run these are equal to 0. Well, the first one is equal to 0 when y is equals to 16 over x squared. And the second one is going to be equal to 0 when x is equal to 32 over y squared. So we wish to solve these two equations, and for that purpose let's put x in here in the first, from the second equation in the first equation, and we will get that y is equals to 16 over 32 over y squared quantity squared, which is equals to 16 over 32 times 32 all times y squared, or y to the fourth, y squared squared. Right? So that's, y equals 0 is not a solution here, so what we get is that y cubed is equals to 32 squared over 16, or 64. 32, we can cancel the 16 and the 32 and get 64 here. And so that y is equal to 4. So the y dimension of this box should be 4. Once we know the y dimension of the box, we can get the x dimension from here, because x is going to be 32 over y squared. That's to say x is going to be equal to 32 over 16, or 2. And once we have the x and the y direction of the box, we can get the z direction from the fact that x times y times z is 24. So that says that z must be equals to 3. And so we now have the 3 dimensions of the box. And it's clear that these dimensions are going to be the ones that make the cost minimal. We want to take a look at another max-min problem. This time let's consider 2 lines in 3-dimensional space and try and find out this distance between the two of them and the points where this distance is obtained. So let's let x equals t, y equals 2t, z equals 3t be the first line. And let's let x equal to 2s, y equals to 2s minus 2, z equal to 2s in the second line. Okay, so we've got these 2 lines in space, right? And we wish to determine where they're closest to each other and where those 2 points are. And so it's schematically something like this. For that purpose, let's take a look at the distance function. The distance between these 2 points is going to be the square root of t minus 2s squared plus 2t minus 2s plus 2 squared, this minus this squared, plus 3t minus 2s squared. Now we wish to minimize this, and it's easier perhaps to let d be little d squared and minimize capital D. To minimize this, we can really just minimize what's underneath the square root, and that of course will minimize the quantity. So if this is capital D, then let's take a look at the derivative, the partial derivative of capital D with respect to t. It's going to be equals to 2 times t minus 2s to the first times 1 plus 2 times 2t minus 2s plus 2 to the first times 2 plus 2 times 3t minus 2s to the first times 3. Okay, the partial with respect to s is going to be 2 times t minus 2s to the first times minus 2 plus 2 times 2t minus 2s plus 2 to the first times minus 2 plus 2 times 3t minus 2s to the first times minus 2. We want to know when these are equal to 0. Right. Well, the first of these is is, well, to simplify things here, we can remove these 2's when we're solving when this is equal to 0 divided by 2. Then what have we got here? We've got t plus 2t is 3t, plus 3t is 6t, so we've got 6t. For s, we've got minus 2s, minus 4s is minus 6s, and minus another 6s is going to be minus 12s. And then here we've got plus 4, that's supposed to equal 0. Down here, setting this equal to 0, we can remove the 2's, and we can also remove these minus 2's here. And we want then this plus this to be equal to 0. That's to say, what do we have? We have t plus 2t is 3t, plus 3t is 6t. Now, there's an error up here. We've got t, in this first case here, plus 2 times 2t is 4t, t and 4t is 5t, plus 9t is 14t, so this first one should be 14t. The s term is going to be minus 2s, minus another 4s is minus 6s, minus 6s is minus 12s, that's okay, and then plus 4. Okay, now here we've got t plus 2t plus 3t is 6t. Now for the s's, we have minus 2s, minus another 2s, minus another 2s, so minus 6s, and plus 2 equals 0. So we want to solve these two equations for s and t. And perhaps easiest is to take this one right here, or this one right here for that matter, and divide it by 2 so that we get 7t minus 6s, this is the top equation divided by 2, plus 2 equals 0. And now if we subtract these two, what have we got? We've got minus t, and 0 and 0, minus t is equal to 0. So t equals 0 is the point where the minimum occurs here. That's to say, on the first line through the point 0, 0, 0, when t is equal to 0 here, what do we have here? We've got minus 6x plus 2 is, s plus 2 is equal to 0, so this is minus 6s plus 2 is 0, or s is equal to 1/3. So at t equals 0, s equals 1/3. Those are the points on the two lines where the distance is minimal. That's to say, that on this line here, it's the point 0, 0, 0. On this line right here, it's the point 2/3. 2/3 minus 2 is minus 4/3, and 2/3 times 2/3, 2 times a third. So these are the 2 points where the distance is minimal, and that minimal distance then is going to be equals to, we can either get it by putting t and s in here, or compute the distance here between those 2 points. It's going to be the square root of 2/3 squared, 4/9 plus 16/9 plus 4/9, or 24, square root of 24 over 3 is the minimal distance. Okay, so there's an example of finding the distance between two different lines in three-dimensional space. I'm going to take a look at another Maximian problem. In this case, let's imagine a piece of sheet metal is to be made into a gutter by making 2 folds of it. And the gutter is supposed to be in the form of a trapezoid, like so. And the total width of the sheet metal make this fold here at an angle theta. And the situation here is that this is going to make sense for x and theta, where x can be any number between 1 and 4, or between 1 and 4, between 0 and 4, and theta any angle between 0 and pi over 2, 90 degrees. So that we're looking at maximizing this on this rectangle right here. Now, the maximum clearly cannot occur when x is equal to 0, so it doesn't occur on that part of the boundary. And it can't occur when theta is equal to 0. If you lay this completely flat, you get no area at all, so it can't occur on that part of the boundary. When x is equal to 4, you make a piece of sheet metal that goes straight up and down here, so it can't occur on this part of the boundary. But it is possible that the maximum will occur on this part of the boundary right here, so we'll need to check that separately. However, what we wish to do now at this point is to write this area here as a function of x and theta. What's this going to be? Well, we've got 8 minus 2x. This rectangle inside here is going to be 8 minus 2x for its base, and it's going to have x sine theta for its height. We have two triangles here. The base of the triangle is going to be x cosine theta, and the height's going to be x sine theta. And since we've got two of them, we just add this on here, and this will give us the total area. Okay, so now we've got a as a function of x and theta. Let's look at the partial of a with respect to x. Right? This is going to be equals to, what have we got? 8x here, so it's going to be 8. We've got minus 2x squared, so this is going to be minus 4x times sine of theta, plus, here we've got x squared, so we're going to have plus 2x sine theta cosine theta. Right. The partial of a with respect to theta is going to be 8x minus 2x squared. I'll plug this out here. Derivative of sine theta is cosine theta plus x squared. Now we've got cosine theta sine theta, so it's the first times the derivative of the second, which is going to be cosine squared theta, plus the second sine theta and its derivative of cosine theta, so this is going to be minus sine squared theta. Right? We want to know in both cases here when this is equal to 0, when these are equal to 0. Okay, ax here, partial a with respect to x has got sine theta throughout, so we can divide by it because we know sine theta is not 0, because 0 is not where the solution occurs here. And so what have we got then? Solving this here for x, we have that minus 8, bring the 8 to the right-hand side here. That's the only term that doesn't have an x in it. And otherwise we've got minus 4x, so minus 4x, and we've got plus 2x cosine theta, so this is going to be plus 2 cosine theta. I'm going to abbreviate cosine theta with c here, and we find that this first equation solves for x, with x equals to minus 8 over minus 4 plus 2c. And the second equation here, we want to remove the sine squared here by replacing with 1 minus cosine squared. So we have the equation all in terms of cosine. And in that case, what have we got? Well, we've got got here is an x throughout, and x is never not equal to 0, so we can divide this through by x here. And we're going to get 8 minus 2x times c, dividing by x, plus x is times c. What have we got here? We've got 1 minus 2c squared is equal to 0. We've got this. This not right. This is minus sine squared, so we should have 2c squared minus 1. So with c representing cosine theta here, then the second equation being equal to 0 is equivalent to h minus 2x times c plus x times 2c squared minus 1 is equals to 0. Let's now replace this with x from the first equation so that we get 2c squared minus 1 times minus 8. All right. Over minus 4 plus 2c plus, here we've got 8c minus 2cx, and x is going to be minus 8 over minus 4 plus 2c. This is going to be equal to 0. Multiplying throughout here by the minus 4 plus 2c, we get minus 32c plus 16c squared. Here, when we multiply here, we're going to get minus 16c. That's plus, well, we have minus 8 times 2, 16c squared, plus 8 is equal to 0. So what have we got? We've got 16c squared minus 16c squared, and we've got minus 32c minus 16c, yeah? This should be, there's an error here. This should be minus 32c and then plus 16c squared. That's okay. Plus 16c. So we've got minus 32c plus 16c is minus 16c plus 8 equals 0. Right? Or c is equals to a half. Right? The cosine of theta is equal to half, since that theta is equals to pi over 3. I suspected an error here because I know that the picture here that's proper for this is that this be equal to pi over 3, or 60 degrees, and that says that this should be made like this, with a 60-degree angle here. Now what about x? Well, when c is equals to a half, x is going to be equals to minus 8 over minus 4 plus 1, or 8/3. So x is 8/3, which means that we should divide this up into 3 equal parts here of size 8/3 here, and that this should be half hexagon. The trough here, or gutter, which has the most cross-sectional area and consequently will hold the most liquid, should be in the shape of half of a hexagon. Now, we still have to consider this possibility over here, namely that what we should do is we should make theta be equal to pi over 2 and make this thing rectangular like so. Make a rectangular trough like this. Now, if you make a rectangular trough, what happens is the following. The maximum for the rectangular trough consists of putting 2 units on each side and 4 on the bottom. Right? This is a calculus 1 problem here, and it's been done before. And so that the maximum area here is going to be equal to 8. Okay? If instead, if we make this trapezoidal trough here with a 60-degree angle here, and 1/3 of the width on each side here, it's going to turn out that this area is going to be larger than 9 for this one right here. You can, of course, compute it by putting the values for pi over 3 back in this formula here, or compute it directly. And so the maximum area is going to be obtained when the trough is made in this fashion right here. We want to look at what's called the second derivative test for functions of 2 variables. It's specific to functions of 2 variables for that matter, and it is not exactly the same as the second derivative test for functions of 1 variable. The reason is the function of 2 variables can be somewhat tricky. What we wish to do is we wish to by considering the second partials of a function f of x and y, we get the partial with respect to x, the second partial with respect to y, and the mixed partials. We wish to derive a test for determining when you've got a maximum or a minimum. For this purpose, let's consider our function f of x and y, and let's take a look at a particular point here, O x naught, y naught, and a unit vector here, u, and let's look at the directional derivative of f of x and y here in the direction u. Well, the directional derivative at a point x naught, y naught, right, is going to be equals to, if u is, let's say, cosine theta, sine theta, it's this unit vector here, then this is going to be the partial of f with respect to x at x naught, y naught, cosine theta, plus the partial of f with respect to y at x naught, y naught, sine theta. And from here on out, I'm going to be abbreviating this by partial with respect to x, c, partial with respect to y, and s for sine theta. Okay, what I want to do now is I want to keep this direction u fixed here. This, if the directional derivative exists, right, this defines a function of x and y. What we can do is we can take the second directional derivative of f in the direction u. All right. What does that mean? Well, this is a function of x and y. What we do is we take its partial with respect to x, dot that with, or multiply that by cosine theta, and a partial with respect to y multiplied by sine theta. So we take the partial of this with respect to x, we're going to get fx x cosine theta plus fyy sine theta. We want to multiply that by cosine theta. now we want to take the partials with respect to y, fxy c plus fyy s. We want to multiply that by sine theta. That's to say what we're doing is we're taking the gradient of this function and dotting it with the vector u. So this is going to be equals to fxx c squared plus f this should be with respect to x, so this is with respect to x. fxysc plus fxysc, so we've got plus 2 fxysc plus partial with respect to y, then with respect to y times s squared. Okay. So now, let's suppose that we've got the partial with respect to x at the point equal to 0. Right? And the partial with respect to y at the point x naught, y naught equal to 0. So we suspect possibly a maximum or minimum here. Now let's suppose that the partial with respect to x and then with respect to x is, let's say, greater than 0 or less than 0 here. And in which case, if it was greater than 0, then we would expect a minimum, because this would mean concave up. If it was less than 0, we would expect a maximum, because that would mean concave down. All right, the question is, if the second partial with respect to x is greater than 0, is it possible that the second directional derivative in a particular direction be negative, indicating that we've got this thing changing signs as u goes around, going from concave up to concave down. So the question is if this is going to be negative, is it possible for this ever to be equal to 0? Right? Well, we're not concerned about when theta is equal to 0 here, because we've already checked that out. So if we divide this through by sine of theta, we're going to have fxx, and now this is going to be cosine over sine, so this is going to be cotangent squared plus 2fxy dividing by sine squared. We're going to get cotangent plus fyy. We want to know whether it's possible that this be 0. If it's going to go from positive to negative as we change around the direction u here, it's going to, and if it's continuous, it's got to go through the value of 0. So we want to know when this is equal to 0. And what? This is a quadratic in cotangent. So this is going to be equal to 0 when cotangent is equal to minus b, let's say minus 2fxy plus or minus the square root of 4fxy squared minus 4 times fx x times fyy over 2 times fxx. Right? So that if this is going to be ever equal to 0, this is going to have to be 0. If it's going to change signs, this is going to have to be 0. That's to say, what we would have to have is that fx y squared subtracted from fxx fyy, right, would have to be equal to 0. If it was not equal to 0, in particular if it was greater than 0, which is what it's going to be here, when we look at fxx, right, if we look at fxx, if this is greater than 0, then no matter which u you consider here, no matter which direction u here, the quantity inside here will always be negative, and so it's not possible for the cotangent to go through 0, and consequently for the second directional derivative to change signs. So if this is greater than 0, then you have an extremum. 0, you can't tell. If this quantity right here at the point x naught, y naught is equal to 0, you can't tell. If it's less than 0, though, then that means that, the directional derivative is going to be able to change signs here, and you will not have an extremum. Right? The point that you do have is sometimes called a saddle point. So if this is greater than 0, then you've got an extremum. If it's equal to 0, you don't. If it's less than 0, if it's equal to 0, you can't tell. If it's less than 0, you don't. Okay? So that the second derivative test for a function f of x and y is first of all to check the partials, make sure they're equal to 0. Check one of the partials and make sure that it's greater than 0. And then if this times this minus this squared is greater than 0, then you have got an extremum. The partial with respect to x with respect to x times the partial with respect to y with respect to y minus this, and this is at the point x naught, y naught. If this is greater than 0, then you have got an extremum, and this is the second partial, the second derivative test for functions of two variables. Well, now take a look at applying the second derivative test for functions of two variables. Let's take a look at a particular function here. F of x and y equals to x cubed minus 3x plus 3xy squared. Right. We're looking for local extrema here, and we want to use this test to determine whether they're local extrema. And recall that the test consists of looking at the quantity fxx fyy minus fxy squared. Sometimes this is written as a quantity delta, and you want to determine whether it is greater than 0, equal to 0, or less than 0. Okay, so here's our function. Let's find the candidates, first of all, for extrema. Let's take a look at the partial with respect to x. This is equal to 3x squared minus 3 plus 3y squared. Okay, partial with respect to y is equal to 6xy. We want to look at where these are equal to 0, and there's the easiest one is equal to 0 when x is equal to 0, or when y is equal to 0. Okay, if this is also supposed to be equal to 0 at the point, and x is equal to 0, then we get 3y squared is equal to 3, or y is plus or minus 1. When this is equal to 0 and x is 0, then we have 3y squared is equal to 3, or y is plus or minus 1. If y is equal to 0 here, all right, then we have 3x squared is equal to 3, and x is equal to plus or minus 1. So this gives us 4 candidates for maxima and minima, local maxima and minima, namely x is 0, y is 0, x is 0, y is 1, x is 0, y is minus 1, y is 0, x is 1, and y is equal to 0, x is minus 1. Okay, so those are the candidates here. Sort of want to make a chart and take a look at the partial with respect to x and then with respect to x. Second partial with respect to y here, the mixed partial, and finally delta. The partial with respect to x and with respect to x here. going to be equals to 6x. The partial with respect to y and then with respect to y is going to be equals to, take the partial with respect to y, it's also 6x. The partial with respect to x and then with respect to y, or y and then with respect to x, is going to be 6y. All right. So at these various points, the partial with respect to x and then with respect to x is 6 times the x value. So here it's 0, 0, 6, 6. Right. The partial with respect to y and then with respect to y is going to be 6x, so it's going to be 0, 0, 6, 6. Partial with respect to x and then with respect to y is the y value here, so it's going to be 6 minus 6. Oops, this should be the x value, so it should be minus 6 minus 6. 0, 0. Okay, 6 and minus 6 and then 0 and then 0. So delta here is going to be this times this minus this squared is going to be minus 36. Delta here is going to be minus 36. Delta here is going to be 36, and delta here is going to be 36. So that indicates that since the partial with respect to x and with respect to x is 6 at this point, right? This indicates what? That you can have concave up as a possibility. The 36 indicates that yes, this is an extremum, and so consequently this is a minimum, a local minimum. Right? The minus 6 here indicates that you've got concave down. The 36 indicates that you've got an extremum, and so that this has to be a maximum. Right? Here you've got negative in both of these cases here, so each of these are saddle points, abbreviating that SP. That's to say, it's neither a maximum nor a minimum. Okay, so there's an example of this function of two variables and the second derivative test. Let's take a look at another. Let's let f of x and y equal to 6x squared y minus 2y cubed minus 3x to the 4th. Okay. The partial with respect to x is equals to 12xy minus 12x cubed. The partial with respect to y is equals to 6x squared minus 6y squared. We want to know when these are equal to 0. Well, this is going to be equal to 0 when x is equal to y or when x is equal to minus y. So x equals y or x equals minus y are two possible things, ways in which the second one can be equal to 0. If x is equal to y, then in the first one here, after dividing through by 12, we get x squared minus x cubed is equal to 0. The only way in which that can happen is if x is equal to 0 or if x is equal to 1. So in this first case here, what we've got are 2 points. X is 0 or x is 1, and consequently y is also 0 or 1 respectively. Yeah? So we've got those two possibilities when x is equal to y. When x is equal to minus y here, where y is minus x, what we get in this case is dividing by 12, and replacing y with minus x here, we get minus x squared minus x cubed is equal to 0. And that can only happen if x is 0 Or if x is not 0, dividing by x squared, here we get x is equal to minus 1. So we get 2 points here. X is 0 and y is 0. And the other point is x is minus 1 and y is 1. So altogether what we've got here are only 3 points. 0, 0. 1, 1. And minus 1, 1. Right? And we now wish to complete this chart here. Partial with respect to x, then with respect to x, with respect to y, then with respect to y, x, y, and finally, the quantity delta. All right? So we want the partial with respect to x and then with respect to x. All right? That's going to be equals to, partial of this with respect to x is 12 y minus 36x squared. Partial with respect to x, with respect to y, and then with respect to y, is going to be equals to minus 12y. The partial with respect to x and then with respect to y is going to be equals to, well, with respect to y and then with respect to x, is going to be 12x. Okay, so at these points here, what are these values? Partial with respect to x and then with respect to x at this point is going to be 0. The partial with respect to x and then with respect to x at this point is going to be 12 minus 36, which is going to be minus 24. Here we've got x is minus 1 and y is 1, so we've got again minus 24. Partial with respect to y and then with respect to y. At this point it's going to be 0. At this point right here, when x is 1 and y is 1, we're going to get minus 12. At this point right here, when x is equal to minus 1 and y is 1, we're going to get minus 12. Right? Partial with respect to x and then with respect to y. Here's going to be 0. Right? This here is going to be 12. And here this is going to be minus 12. Right? The x value times 12. Okay, so now how about delta? Well, here delta is equal to 0, so you can't tell. Right? Here we've got this times this minus this. 24 times 12 is going to be 288 minus 144 squared. This is going to be 144. So that's positive. fxx is negative here, and so this says that what? Negative means concave down, so a maximum here, huh? Right? Here we've got 24 times 12, that's 288. And now we've got minus this squared. So this is 144, right? And so what? We've got a negative here, right? And this is positive, so this is also a maximum. Right? So these are relative maximums. You can't tell what's happening at 0, 0 here for this function using the second derivative test. So there's the second derivative test, 2 examples of it. We're going to take a look at the method now for finding maximums and minimums on either a curve or on a surface of a function of x and y, or a function of x, y, and z. So if we've got a function of x and y, right, and we've got a curve x and y equal to a constant. That's to say it's a level surface, level curve for a function g. Or another situation we're going to look at here is if we've got f of x, y, and z, defined in three-dimensional space, we want to know where it's maximal and minimal on the surface defined by a function g of x, y, and z equal to a constant c. All right. The curve here, or the surface, sometimes occurs when you're trying to find a maximum or minimum of a function on a region, and you have got now to consider the boundary of this region also, and that sometimes is the curve or surface that you're interested in. Sometimes you're just simply interested in finding the maximum or minimum on a given curve or surface. The first situation here is in the plane, and you've got some sort of g of x and y equal to a constant on this curve. The second one is in three-dimensional space. You've got some sort of a surface here then, where this is the surface where g of x and y and z is of a particular constant value. The idea is to, in either case, look at r of t, a parametrization of a curve that lies in the surface, or in this case here, r of t, a parametrization of a curve that runs along this given curve. And notice the following here, that if we look at f of r of t, right, we can differentiate this. This is a function of t, and we can differentiate it as follows. The derivative of this is the gradient of f at r of t dotted with the derivative of r at t, because it is equal to the partial of f with respect to x times the derivative of x with respect to t plus the partial of f with respect to y times the derivative of y with respect to t. And if there's three variables involved here, plus the partial of f with respect to z times the derivative of z with respect to t. In either case here, with either two variables or three variables, this is the gradient. The gradient is partial with respect to xi plus partial with respect to yj, dotted with the derivative, which is dx dt dy dt. And then if there are three variables, then this term here will also occur. Well, we want to know when the derivative is equal to 0, and so we would like to set this equal to 0 because that's when you expect maxima or minima to occur, assuming that this is differentiable. Right? Well, let's take a look at the following situation here also. G of r of t is equals to, the derivative of this is equal to the gradient of g at r of t dotted with r prime of t. Right? Well, g of r of t, if you're on the surface here, is equal to 0. So you want to let this be equal to 0. This is equal to 0 because what? G of r of t is a constant. Okay? So, what this means is, well, there are a couple of interpretations you can make of this. One of them is the following, that if we look at the gradient, no matter what r of t you've got passing through this point here, the gradient dotted with r of t is automatically going to be 0 on the level surface. That means the gradient is perpendicular to the level surface. So this is the gradient of g. As long as it's not equal to 0, it's perpendicular to the level surface. And this allows you to find a tangent plane. This is a totally different problem here. If you can find a tangent plane using the fact that the gradient g is perpendicular to the surface. You then have the gradient is normal to the level surface, and this will allow you to find the tangent plane. But that's not what we want to do right here. What we wish to do at this point right here is we wish to find at what points is the gradient of f equal, dotted with r prime of t equal to 0, right? And if at a point x naught y naught on the curve, or x naught y naught z naught on the surface, if we have the gradient of f at x naught y naught, or at a point x naught, equal to a multiple of the gradient of g at x naught, right? Then the gradient of g dotted with r prime will be a multiple of the gradient of f dotted with r prime. Since this is always equal to 0, then this will be equal to 0. So if there is a lambda, so that this happens, then we will have the gradient of f dotted with r prime equal to 0, because the gradient of g dotted with it is equal to 0. Now, the other possibility is that the gradient of g is equal to 0. So the thing to check here are two different types of points. One is where the gradient of g is equal to 0, and the other one is where it's not. If the gradient of g is not equal to 0, and we can find the lambda, so that the gradient of f is lambda times gradient of g, then that will be a candidate for max minimum. The other possibility is that the gradient of g is equals to 0, and you need to check points where the gradient of g is equal to 0. Usually it won't be. What does this consist of? This consists of the fact that we're going to have several equations to solve. The first one is going to be simply that g of x and y, for example, is constant. The second one is that the gradient of f is going to be a multiple of the gradient of g. So we're going to have the partial of f with respect to x at x and y is going to be some multiple of the partial of g with respect to x at x and y, and the partial with respect to y at x and y is going to be the same multiple of the partial of g with respect to y at x and y. That's to say, in this case here, on a curve, we've got three equations and three unknowns. C is supposedly known, so what we've got for unknowns are lambda, x, and y. If we can solve these for lambda, x, and y, we get the candidates for maxima and minima along this surface. Whichever value is largest is the maximum, whichever is smallest is the minimum. We're looking at functions of three variables. We have a similar situation. You have g of x, y, and z equals to a constant. That's one equation. The other equation is the partial with respect to x at x, y, and z is a multiple of the partial with respect of g with respect to x at x, y, and z. Right? The partial with respect to y at x, y, and z is the same multiple of the partial of g with respect to y at x, y, and z. And the partial with respect to z at x, y, and z is the same multiple of the partial of g with respect to z at x, y, and z. So in the three-dimensional case, what we have is four equations and four unknowns. We can solve them for x, y, z, and lambda. Usually you don't really care what lambda is, but frequently you end up finding it anyway. We can find all the solutions to these for x, y, z, and lambda. Then the x, y, z are the candidates for maxima and minima along the surface. Right? And checking them will determine which is maxima and which is the minima. Now let's first take a look at a simple example of Lagrange multipliers for finding maximum and minimum. Let's take a look at the function f of x and y, let's say, is equal to xy, x times y, subject to g of x and y, x squared plus y squared equal to 4. That's to say, we want to maximize this, find the maximum and minimum of the function x times y on the circle radius 2. Where does x times y take on its maximum and minimum on that circle? All right. So what we do is we take this as one of our equations, namely that x squared plus y squared is equal to 4. And for the other equations, we take lambda gradient f is equal to lambda gradient g. All right. The gradient of f is partial of f with respect to x, which is y, and this is supposed to be equal to lambda times the gradient of g. Partial of g with respect to x is 2x. Right? If gradient f is lambda gradient g, then the partial of f with respect to y, namely x, is supposed to be lambda times the partial of g with respect to y, which is to say times 2y. So what we have here then are these three equations in the three unknowns, lambda, x, and y. What do we get here? Lambda from the second equation here is equals to y over 2x. Okay. From this equation here, y over x is equal to 1 over 2 lambda. So that y over 2x is going to be equal to 1 over 4 lambda. So we get 1 over 4 lambda is equal to lambda, and now so we get lambda squared is a quarter, or lambda is a half. So this gives us then y equals x, or y equals minus x, are possible places where maximum and minimum occur. Now, if we now go back here to the fact that we've got x squared plus y squared is equal to 4, if y is equal to x, then what have we got? We've got 2x squared is equal to 4, or x is equal to the square root of 2 plus or minus the square root of 2. If y is equal to minus x, again we've got 2x squared is equal to 4, and x is equal to plus or minus the square root of 2. So altogether here we end up with 4 candidates here. X can be either the square root of 2, and y equal to x, the square root of 2. X can be the square root of, minus the square root of 2, and y equals to x, which is minus the square root of 2. X can be the square root of 2, and y equal to minus x, so minus the square root of 2, and x can be equal to this minus the square root of 2, and y equal to the square root of 2 here. If x is minus the square root of 2 and y is minus x, we have this case right here. Now what's the value of the function x times y? Well, in this case here it's equals to, f is equals to, 4, 2, right? Here it's equal to 2, here it's equal to minus 2, and here it's equal to minus 2. So f of these points here are 2, 2, minus 2, and minus 2. And so that says that at this point here, the function is maximal and its value is 2. It's also maximal over here, its value is 2. So these are the max. And the minimums are over here at 2 minus the square root of 2, where the value of the function is minus 2, and over here where the value of the function is minus 2. So these are the minimums. So there's an example, a simple example illustrating Lagrange multipliers. subject to the restriction that g of x, y, and z equals to x squared plus 2y squared plus 3z squared, would this be equal to 4? So this right here is the graph of an ellipse. It has for its graph an ellipsoid, I should say. And we now want to know, where does this function take on its maximum and minimum on the surface of that ellipsoid? And for that purpose, we want to solve this equation right here, along with the three equations that we get by writing the gradient of f is the constant multiple of the gradient of g. Right? That's to say, we're going to write the equation partial with respect to x is lambda partial of g with respect to x, partial f is lambda partial of g, partial f with respect to y is lambda partial of g with respect to y, and partial f with respect to z is lambda partial of g with respect to z. These three equations, along with this one, in the four unknowns, x, y, z, and lambda. All right, partial f with respect to x is 1, and so that's supposed to be equals to lambda times the partial of g with respect to x, which is 2x. Partial f with respect to y is also 1, and that's supposed to be equal to lambda. Partial of g with respect to y is 4y. Partial f with respect to z is 1, and that's supposed to be equal to lambda times the partial of g with respect to z, which is 6z. Right? So we've got these three equations right here, along with this one. We wish to solve them and find the possible solutions of x, y, and z, and these will be candidates for the maximum and minimum. We mentioned that it's not always easy to solve four general equations in four unknowns. However, here, let's solve this for lambda, in which case we get, let's solve this for x, in which case we get x is 1 over 2 lambda. Here for y, we get y is equals to 1 over 4 lambda. And for z, we get z is equal to 1 over 6 lambda. All right. Now if we put these three values in here for x, y, and z, we get 1 over 2 lambda squared plus 2 times 1 over 4 lambda squared plus 3 times 1 over 6 lambda squared is supposed to be equal to 4. Right? That's to say, we get 1 over lambda squared in each case here, so we can write 4 lambda squared is equals to 1/4 plus 2 over 16 plus 3 over 36. Right? That's to say 1/4 plus 1/8 plus 1/12 here, right? All right. Well, this is what, so many 24ths? There's 6 24ths and 3 24ths and 2 24ths, or 11 24ths. This is supposed to be 4 lambda squared, so we get lambda squared is equals to 11 over 24 times 4, 96. And lambda is the square root of 11 over 96, plus or minus. Now we don't really want lambda, what we want is x and y. And so when lambda is equal to plus the square root of 11 96ths, we get x is equals to 1 over 2 square root 11 96ths. Y is equals to 1 over 4 square root 11 96ths. Z is equals to 1 over 6 square root of 11 over 96. And for the plus, these are clearly the maximum. That's to say this function right here takes out its maximum when all of these are plus. Right? The minimum is going to be when all of these are minus. Right? So 1 over minus minus 2, 1 over minus 4 square root of 1196, and 1 over minus 6 square root of 1196 is going to be the minimum. 1 over 2 square root of 1196 minus 1 over 4 square root of 1196 and minus 1 over 6 square root of 1196. This is the minimum. Here's the maximum here. Okay, so here's another example then of how to use Lagrange multipliers to find the maximum and minimum of a function on a surface.